So thank you very much for the introduction. So I'm indeed Julien Vergos from CA, the French NDC, and it's a real pleasure to be here. And the performances of the performances of infrasound networks are highly variable, okay? And they are by far the most variable of the three waveform technologies. And so tracking or capturing its fine-scale structures in operations remains a real challenge today. That's why today I'll share with you our latest work about the assessment of the infrasound IMS network, and this for near real-time applications. Okay. So the IMS infrasound network is a unique global network, and it has expanded a lot during these past 25 years. You can see on the graph at the top the evolution of the number of certified stations over time, and the color of the stations which indicate this certification date. Today, the IMS infrasound network is 90% complete. So there are 54 stations which are certified out of 60 which are planned. And it provides very high quality and data and very high data availability. And after 5 years without any new certifications, the last station, so IS-16 in China, has joined the network. And this network clearly offered the opportunity to track the performance, how it evolves with time, and to see how performance are going greater and greater when the network grows denser. So compared to previous studies, really here the objective is to assess the IMS infrasound network detection capability for atmospheric explosions with a better precision. And this under operational constraints. We are talking about near real-time application, and so with limited computation costs. And to reach this precision, we want to take into account realistic explosive source spectrum, also frequency-dependent distribution for the transmission losses. So for example, in contrast to Le Pichon's work, we choose scaling laws. We want to use realistic atmospheric specifications, this time in contrast to Green, which use climatology, and also to account for frequency-dependent noise levels, data availability, and this at the arrival time of the waves. And this in contrast to Blom, its last paper, when he considers monthly noise models. So from hours to hours, from season to season, from a region to another, the detection capability can dramatically change. And it is due to propagation or noise conditions. And a good tool to study this variability is DTK device, which is part of NDC in a box. You have a snapshot here. So please, if you're interested, just behind the door, you have booth 3. We'll make a demo with pleasure. So I won't go into detail for the equation, but the chosen methodology here is a statistical framework which is inspired by recent works from Blom and Le Pichon. So the idea is the following. So for a given yield, we compute spectral levels at the source, and these are different frequencies. From these spectrum levels at the source for the different frequencies, we calculate propagation-based probability distribution at each station and for each of these frequencies. So we have distribution of the signal at each station. On the other side, from the PSDs, we calculate the probability distribution of the noise. And from these two distributions, so the signal and the noise, we calculate the probability that the noise at the station, at each station, has a spectral amplitude less than or equal to that of the signal. And this equation which is framed. And in this study, we consider that we detect a given yield if the detection probability is at a station is greater than 90%. So we have chosen a time resolution for the noise of 1 hour. And for this, we have calculated more than 60 million of PSDs, this from 20 years of raw waveforms of all IMS stations. And this represents about 5 terabytes of data. We also need station metadata. And I insist on this because, of course, during these past 20 years, stations have changed. And we have to take into account these changes over time. For the atmospheric specifications, we use ECMWF, so Integrated Forecast Systems Analysis, which represents about 1 terabyte of data. And if you're interested in the calculation of the for the PSDs that we computed with DTK quality. Please, we can make you a demonstration on the stand, and you can also see Ishrak Ketata's poster by PTS. So it's on a Friday morning. Concerning the algorithmic complexity, okay, we have 5 nested loops. For each yield, for each frequency, for each station we change over time, for each source grid, and for each time step, we need to compute this detection probability. And so we have chosen a time resolution of 3 hours. The source grid resolution is 1 degree, the station, so from 20 to 54. 16 values for the frequency, and 100 value for the yield. Sorry, and this led to the computation of 3 trillion of transmission lots, which is very much. So finally, the total time for computation for the simulations were about 4 weeks on a very good machine. Okay, it's a server. For unitary costs of 40 seconds, so to produce 1 time step. So the size of the database or the results is about 15 gigabytes, and it's compatible with operational implementation. Okay, so now the data. So here is a fast overview of 20 years of data availability. We could say a lot of things about this. So you have the 54 stations along the y-axis. They are sorted by latitude, and you have 20 years on the x-axis. So what we could really highlight is that the gaps with time are more and more numerous. Okay, you can see on the top panel that the number of operational stations, which is a red time series, is closer and closer to the number of certified stations, and thanks to the very intense work of IMS staff. And however, there are some gaps which are remaining, and taking into account these gaps is very important. And here is the same thing for the noise this time. Okay, so on the map you have all the stations. The color is the mean noise levels, station noise levels at each station. So averaged over their certification date. And you can see that you have a lot of difference from station to stations. And after you have a 20 years view, you have a 1 week view, and the main message of this is just a mess. Okay? You have a lot of differences from station to station, and for given stations, the noise levels really fluctuate across seasonal, diurnal, and hourly time scales. You can see that 20 years or 1 week, it is the last week of August, so 2 weeks ago, is the same story, and we have to take this into account. And if you want more detail, please visit Patrick Hoop's poster. You have a dedicated poster about infrasound noise at IMS infrasound station. And here are the results of 20 years of global simulations, so displayed as detectability time series at 1, 2, and 3 stations. So what we plot here is the explosive yield, so along the y-axis, the explosive yield detectable on 95% of the Earth surface as a function of time. And in the background, you have the number of operational stations, so which take into account the data availability. So a lot of things to say about this, but overall, you will see that network performance improved substantially over time. When you track the minimum values of each curve, it clearly decreases every time you have a new certified station. And you also see that before 2012, there were a lot of times where the 1 KT was exceeded, and that now, so since 2021, there are only some very rare times where this threshold is exceeded. You have some very clear seasonal variations, which are associated to propagation effects, and with more than 1 order of magnitude from one season to the other season, and also a very high short-term scale threshold variability. Okay, it's the line thickness. And so if we consider only the last period where the number of stations was stable, so between 2021 and 2025, the 2 stations threshold vary between 80 tones and 600 tones, and the 3 stations threshold vary between 100 tones and 2 kilotons. And if we consider only 90% of the globe, so 1 KT is detected at 3 stations. Okay, actually behind each time step, a map is hidden. Okay, it's just statistic on the maps. And so if you want to access the detail of what is hidden behind each point, we need to display this kind of map. So here in the time series, we zoom on 4 years, the 4 last years. between 2021 and 2024. So we see very well the seasonal variations. And we see that we have peaks, okay, sudden peaks which exceed this 1 KT. And we want to have access to the detail of why in March 2024 we have this. We display the map, which is we see on the top. And here actually, and this is the same story for all of the peaks, you have a poor detectability when you have a simultaneous combination of unfavorable propagation condition, high station noise, and non-operational stations. So in that case, you can see that in the south hemisphere, all the stations are red. You have a high noise, okay? The stratospheric winds has arrows. They are small, so poor propagation conditions. And at the same time, you have 2 offline stations in South Argentina and in Australia. And this, the conclusion of this, is that you have a poor detectability for that date and regionally in the south hemisphere. And it's the case for all of the peaks except one. And this one occurred in January 2022. So here we have a zoom in the time series on 10 days between the January the 10th, 2022 and the January the 20th. And you have to see a peak exactly the 15th of January at 4, which is the time of this megatonic explosion eruption. And you can see on the map that the detectability is really affected in the vicinity of the volcano. And it is the only event actually which impacted the event, not the noise, which impacted globally the performance of the IMS network. Okay, now here's a 45-second movie, okay, condensing 2 decades of detectability at 3 stations. You see the variability in space and time. Okay, what you can see is that it's a mess. You have a high variability so in time. So every time you have a new stations are blinking a lot because they are associated to the noise levels, which are changing very fast. Every time you have a new station, it pops on the map on black. And what you see overall is that when you look at blue areas, okay, these blue areas are always deeper and deeper blue, which means that the detection capability are improved with time. And after, if you look at the details, you have 1 year is 2 seconds. You have, okay, so every second you see the seasonal variations, which are associated to propagation to the conditions. But if you want to have more detail about this, download this presentation and look at it frame by frame or in slow motion. Okay, so now if we focus on the 1 KT detectability, so at 3 stations, so we represent it at the percentage of Earth coverage on the top panel, the time series, and at the fractions of times for which the 1 KT is detected in five time intervals. Okay, and also what we can see that the detectability levels are better and better. So you detect. So be careful. Black means that you detect 1 KT less than 90% of the time. Okay, on the core scale, not 0%. And just to compare, now we can see that where the regions where detectability remain the poorest is close to the equatorial region, and in particular close to China, Iran, and India. But these places are exactly where stations are planned. Okay, so this seasonal effect, once again, if we look at the performance as the function of the season, you have a better overall performances during the winter, so during and the summer, so at the solstices on the left, and worse performance, especially in autumn, as you can see on the left. But that these thresholds are highly variable, okay, because of the noise, and this variability persists across all the seasons. And it is an extra slide just to show you the preliminary estimations for the 3-station detectability gains from the certification in China, because it's where we can see we had a poor resolution, or the poorest coverage. So we have 2 maps, okay, so taking into account, without taking into account this station, taking into account this station, and you have a differential map. So on the log scale, you cannot see a lot of things. Okay, but when you look at the differential map in linear scale, we can see that regionally, thresholds can drop by up to 500 of tones. Of course, this has been done on 6 days of data because it's certified, and a longer data set is needed to fully access the contribution of this station for the MS network. So, the conclusion. So we have implemented a statistical framework just to assess the detection capability and uncertainties with more realistic precision. And we have applied this to 2 decades of IMS infrasound data. So the main conclusion is that these thresholds are highly variable. And this from season to season, from 1 hour to another, from one region, etc. Okay? But our conclusion is also that these 53 stations, which deliver high-quality data, a 1 KT explosion is already globally detectable, even if, indeed, we still have some temporal and regional gaps that are more pronounced at the solstices. But we expect improved performances from the full network, so of 50 stations, and it is already evident with ADS-16. So the next step, just to put this in operation in the French NDC. This should be done in the coming months, and this implementation should be very useful for civil applications. Also, to incorporate new approaches based on machine learning techniques, so AI, to calculate transmission losses, so to take into account range-dependent atmosphere, to take into account the thermosphere, which is not parameterized in that model, just like a Camejo paper, please read it, and to account also for station-dependent detector performance, so typically for MCML, we can have a similar to those of ratio of detection, and also to perform sensitivity studies on the middle atmospheric fine cell structures. Thank you very much for your attention.